Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about experimental tests of Bell's inequalities. So, what's that all about? Well, last week you read this wonderful article by David Merman called Is the Moon There When Nobody Looks? And that article featured a Gedanken experiment, a thought experiment that you could do to highlight what Bell's theorem and Bell's inequalities were all about. And then last week in tutorial, we tried to connect that Gedanken experiment to something that resembled a real experiment, similar to the one that we do down in the laser lab. But this week, you're going to be reading an actual journal article that tells how to do these experiments. So there's this article that also appeared in the American Journal of Physics from a group out at Reed College in Oregon called Entangled Photons, Non-Locality and Bell's Inequalities in the Undergraduate Laboratory. And you're going to read this and you're going to sort of get into the nitty-gritty a little bit. You're going to actually see what you actually have to do to perform these experiments and test to see whether quantum mechanics is correct or whether you need some sort of hidden variable theory to explain the experimental phenomenon. So let's dig in. Okay, so just a few words of advice as you go to read this paper. As any journal article, it's challenging. There's a lot of detail and stuff that you may not know in advance. So one general bit of advice is try not to get too lost in the details. Try as much as possible to see the big picture. One challenge is just notation is a little bit different in this paper than the notation that Beck uses, and you want to make sure that you don't get too thrown by that. So, for example, in the Beck text, and also when we've been talking amongst ourselves in tutorial, we've used a notation for this joint probability. We've called it P theta sub s, comma, theta I, and then sometimes you'll see a perpendicular sign up here. And what Beck means by that is it's a joint probability that for the if the polarization analyzer on the signal channel is at angle theta sub s, and the polarization analyzer on the idler channel is at angular position theta sub I. This is the joint probability that the signal photon will come out the top port and the idler photon will come out this bottom port, the theta sub I plus 90 port, or theta sub I perp. Okay, well, that's the idea, but the notation is pretty arbitrary. So that's what Beck decides to use. When Dellinger and Mitchell, who wrote the HAP paper, want to express exactly the same idea, they would call this quantity P sub HV and then alpha beta. So that just means that they've chosen to call the angular orientation of the analyzers. Those angles are called alpha and beta, and then the HV here is Dellinger and Mitchell's way of saying this is the probability that the signal photon comes out, what corresponds to this port on the polarization analyzer, and the V here means that the idler photon is coming out along the bottom port. So it is just a change in notation, nothing deep here, but you don't want to get thrown by that. And then the larger sort of issue is there is a bigger idea here, is that as you begin to read journal papers instead of textbooks, there are going to be all these notational differences. And you just have to learn to deal with them and not get too thrown by them, even though they can sometimes be very annoying and confusing. It's just part of life to deal with it. So as you read through the paper, again, there are lots of technical details if you really want to understand what's going on in this apparatus. Well, uh, you should try as best as you could to understand as much of it as you can. But the more important thing is to really focus on the big idea of what the point of the paper is. And I've sort of highlighted in the abstract here a sentence, and this sentence here asks, to sort of try to understand as best you can what the sentence means, because this is really the key conclusion of the paper. A test of the Clauser-Horn-Shimony and Holt version of the Bell inequality finds S is equal to 2.307 plus or minus 0.035 in clear contradiction of hidden variable theories. Well, what the hell does that mean? It's an important sentence, but its meaning may not be immediately clear to you. So let's spend a minute or two trying to understand what this sentence means. So the issue of Bell's theorems and Bell's inequalities has to do with providing a way to distinguish between two different types of physical theories. One is quantum mechanics, which is based on this idea of non-determinism, and sort of reality doesn't exist until you make the measurement, the so-called Copenhagen interpretation of things, versus theories that are called local realism, or sometimes hidden variable theories, where there is this objective reality even before you make the measurement. And the general structure of all these situations involving Bell's inequalities, I can summarize with a little picture here. So there's some physical quantity, which we'll call X, something that you can measure experimentally and predict theoretically. And let's say quantum mechanics calculates what this quantity should be, and it makes a prediction as to what the value of this quantity should be if you were to go and measure it. We'll call that particular value X sub QM. And then the sort of analysis that Bell did, if you use that analysis and you assume some sort of local realism or some sort of hidden variable theory, generally you can say, well, X can take on a possible range of values, but it might not be able to exceed some maximum value. So the Bell's inequality that we would write down for this situation would say that according to any hidden variable theory, the value of X has got to be somewhere in the range less than some upper bound, which we'll call C. And if you're an experimentalist, you look at this state of affairs and you say, great, great. If it really is like this, I can go do an experiment. I can measure X. And quantum mechanics is making a prediction that X should have a value of this. And the hidden variable theories say, no, 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 it's got to be this. And you can go and you can make a measurement and you can see which type of theory is in accord with your experimental observation. So if you go and make a measurement, you're going to get some sort of experimental value. And let's suppose the experimental value that you measure, and we'll call this value X sub EXP, the experimental value. But of course, when you make an experimental measurement, there's an uncertainty in your measurement. And I'll express the uncertainty by this shaded red arrow here. So you would generally express your experimental result. You would say, something like the value of X is equal to some experimental value, but plus or minus some uncertainty, which we generally call sigma. And if you get a situation that sort of looks like the one I've sketched here, you would say, well, my experimentally measured value of the quantity X, if you take into account the uncertainty of my measurement, that overlaps with the prediction of quantum mechanics, but it doesn't overlap with the range of values that the hidden variable theories predict. So you would be able to say, if this was the result of your experiment, you would say, well, my experiment supports the predictions of quantum mechanics, but is in contradiction of the predictions of the hidden variable theory. So we would say the jargon would be to say that the experimental result violates the Bell's inequality because the experimental values don't lie within the range of possible values that Bell finds for any hidden variable theory. So this experimental result would support quantum mechanics and argue against local realism. So in the AJP AJP paper that you're reading, the particular Bell inequality um, that you're investigating is something that is due to researchers named Clauser, Horn, Shimoni, and Holt. And just as a parenthetic aside, Abner Shimoni was my next door neighbor for 20 years, right on the edge of the Wellesley College campus. He was a physicist from Boston University. I lived in faculty housing on the Hoyden Golf Course, and he lived right across the street, and I got to know him pretty well. And I only realized I knew he was a pretty good physicist. I've only really come to realize in recent years he was really a pretty did some pretty important work, and his name is all over the place with the early work on Bell's inequality. He was early to the game. Shortly after Bell published his paper, Abner sort of saw the importance of it and wrote some seminal work. And Abner's wife, Anne Marie Shimoni, taught at Wellesley College for many years, so that's where they were living right next to Wellesley College. Anyway, an amusing side note. Anyway, back to the main story. Abner and his friends identified this quantity, which is called S. S here got cut off. S. And they concluded, and you'll see when you read the paper how to calculate S. It's derived from the sort of joint probabilities that you can measure experimentally. And Abner and his friends concluded that if you had a hidden variable or local realism, any local realism based theory, the value of S had to be less than 2. So Abner says S is less than 2, and Dellinger and Mitchell go and do these experiments and measure S experimentally, and they are finding a value of S equal to 2.3 with an uncertainty of 0.35. So the smallest value S could have would be 2.307 minus 0.305, and that number is clearly much bigger than 2. So their experimental results are a clear contradiction of hidden variable theories. And if you read the paper a little bit more, you'll also see that the value that they get is entirely consistent with the predictions of quantum mechanics. So that is that. And then in the fourth and final slide, I point the way towards this article that is linked on problem set 4 by none other than Elaine Aspect, a relatively recent article, summarizing, he spent his career worrying about these things, and there's been a lot of progress, a lot of talk about just broadly what the loopholes are, and this sort of possible conspiratorial type things about how these experiments could be missing something, and all of the possible sort of loopholes have now been closed, and sort of it's an experimental fact that quantum mechanics agrees with experiment, and any sort of hidden variable theory that you that is possible is in contradiction with well-established experimental facts. So that's closing the door on the Einstein and Bohr debate. Einstein loses the debate. Bohr is the winner by unanimous decision of the referees. And then the sort of pointing the way. This last sentence of the abstract is close one door, open another, opening the door for new quantum information technologies, which is what we're going to be talking about, things like quantum computing, and that's where we're headed in this course. So that's the big idea. And then let me just finish up by saying there's an article which is actually linked from problem set 4, which you might want to take a look at. There's a quote at the beginning of problem set 4, this quote here. The article is written by none other than Elaine Aspect. Aspect, you may recall that name. This was the experimental work that was quoted in the 1985 paper by David Merman, Is the Moon There When Nobody Looks, the paper you read last week. And Elaine Aspect was a rather young experimental physicist who was provided one of the most earliest convincing tests, experimental tests of these Bell's inequality using entangled photons. And Aspect and a whole generation of people have made careers out of refining these measurements and trying to really nail down conclusively the fact that hidden variable theories are not consistent with the observable world and that quantum mechanics is. So there have been this whole series over the decades of experiments trying to close these so-called loopholes. People can come up with all sorts of, they can concoct these crazy, almost conspiracy theories about how hidden variable theories might still be viable. So you have to work very hard experimentally to rule out all the possible loopholes. But I think there's broad agreement in the field now that the experiments are really conclusive. The door has been closed on this now uh, nearly 90-year-old debate that Einstein and Bohr started in the early 1930s about whether quantum mechanics or local realism was the true theory of nature. And the verdict is in. Einstein is the loser of the debate. Bohr is the winner by unanimous decision of the referees. So it's nice to have some sort of closure on that important matter. But as we read here, as one door closes, another door opens. We really do understand that entanglement is a real thing. And not only is it real, but it is potentially quite useful. It opens the door to all sorts of new applications in quantum information, things like quantum computing, which is the next big topic that we will be tackling in this course. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.